This video was sponsored by Let's Get Rusty. A couple of weeks ago, a post from Riot Games went viral after they started making hardware used for cheating practically unusable. And of course, a lot of people got mad, accusing Riot of deliberately sabotaging users' computers. So today, we are going to cover the basics of how some game cheats work, what game companies are currently doing to detect them, and whether they really have the power to make users' computers unusable. Hi friends, my name is George, and this is CoreDumped. Game developers have had to deal with cheaters for decades at this point. Traditionally, game cheaters operate by installing either a modified version of the original game or additional software that somehow gives them an advantage. That advantage, of course, depends on the game. For example, in some games, it could mean giving the player unlimited in-game currency or infinite health points. You know, things that make progression easier and faster. So, in a way, it only affects the cheater. However, in competitive multiplayer online games, like shooters or MOBAs, whatever advantage the cheat provides becomes a much bigger problem because it ruins the experience for other players. Cheats like wall hacks, vision hacks, aimbots, and many others give advantage to the cheater, but it makes life miserable for other players. I've been there. These cheating mechanisms are possible because the match is actually being played on a server, and that server often sends player position data to everyone in the match, including information about the enemy team. But it is the local game logic that decides which players should actually be visible and which ones should be hidden, depending on things like distance, walls, fog of war, or whether the enemy is inside your field of view. It is almost like the players are streaming what is happening on the server, but each local client decides what to show to each player based on their perspective inside the game. The reason many games are implemented this way is because of latency and prediction. Imagine you are playing a game where your character has a limited range of vision, and an enemy is walking toward you. If some information about that enemy is already on your computer before they become visible, the client can render them immediately as soon as they enter your vision range. However, if the server does not send any information about hidden enemies, there would be an additional delay between the moment the enemy enters your range of vision and the moment your computer receives enough data to actually render them. That delay could make the enemy appear late, pop into existence, or show incorrect movement or animation. Because of this, games often send more nearby or possibly relevant state than what is visually visible at that exact moment, so the client can render the game smoothly and responsively. This is why you can immediately spot enemies when peeking around a corner, or why they become visible right away when crossing a visibility boundary. So when you play online against other people, information about enemy positions is often already available on your computer. It is just not being shown to you. What a lot of cheats do is exploit this fact. They read that information from the game's memory and simply show it to the cheater. And just like that, enemies behind walls become visible, resulting in the infamous wall hack. The same principle can be used to reveal or hint at the position of every player on the map, resulting in what many people call a vision hack. Or a more complex script can be used to automatically aim at and shoot enemy players, which is commonly known as an aimbot. Now you might be wondering, how exactly is any of this done? Well, there are various methods. But before talking about that, if you follow this channel, I'm pretty sure you love low-level systems. And that's exactly why I'm excited to say that this video is sponsored by Let's Get Rusty. Big companies are betting big on Rust for building critical systems. Google, Microsoft, even the Linux kernel itself are now integrating Rust into their core systems. That's not hype, that's happening. And if you're thinking about leveling up your Rust skills, whether for personal growth or to land a job working on real systems, Let's Get Rusty is the go-to place for Rust training. Created by a fellow YouTuber and one of the most beloved names in the Rust online community, Let's Get Rusty has helped thousands of developers, myself included by the way, master the language and break into systems programming. They're running a new cohort very soon, and since spots are limited, now's a great time to check it out. Visit letsgetrusty.com/startwithgeorge, or just click the link in the pinned comment below. And now, back with the video. One cheating method is code injection. Programs often come bundled with dynamic libraries that are loaded at runtime. A cheat can replace one of these libraries with a modified version. Later, when the game runs, it asks the operating system to load that library, which is essentially additional executable code. and since the cheat ends up running inside the game process, it can manipulate the game's rendering logic to do things like showing enemies. Another known approach is hooking the graphics API used by the game. Most gamers know that between the game and the GPU, there is a layer known as the graphics API, DirectX, OpenGL, Vulkan, Metal, or whatever the game uses. For those who are not familiar with this concept, a graphics API is basically a programming interface designed to help render computer graphics to a monitor. The game provides the assets, and the graphics API renders those assets according to how the game tells it to render them. So, showing the image produced by a game is not a single task, it is a pipeline. Many known cheats do not need to understand the game's internal logic. They can simply hook into the rendering pipeline and change how certain objects are rendered. For example, they could tell the graphics API to skip the depth detection step. As a result, the cheat modifies the render state so walls no longer hide enemies behind them. Not because the game itself has been altered, but because the part of the rendering pipeline in charge of calculating whether something is behind another object has been bypassed or disabled. Other cheats work by overlaying data on top of the image produced by the game. I am pretty sure most of you have seen programs that overlay system data on top of a game, like FPS counters, temperatures, CPU usage, or GPU usage. That same kind of feature can be abused by cheating software. The cheat reads the game's memory externally, gets enemy coordinates, and then draws boxes, markers, or skeletons over the game window. That is, in fact, how a lot of early vision hacks in games like League of Legends worked. Now, for those of you with more technical knowledge, this might sound impossible because operating systems implement processes as isolated bubbles. Usually, one process cannot directly access the memory assigned to another process. But operating systems also provide legitimate tools for debugging and inspecting running programs. Through specific APIs, and with enough permissions, one process can ask the operating system to open another process, read parts of its memory, and sometimes even write to it. These mechanisms exist mainly for debugging, especially during software development. But while debuggers use them for legitimate reasons, user-level cheats abuse the same idea. They attach to the game process, search for useful values like player positions, health, or camera data, and then read or modify those values while the game is running. Now, these are only a few examples of how game cheats can be implemented in software, and if you have technical knowledge in this area, you probably know that all of these mechanisms are detectable. However, my main purpose in this first part of the video is simply to show that, from a programming perspective, there is not one single way to write cheating software. There are many ways to do it. If we already know how a cheat works, writing software to detect it may seem trivial. But if we do not even know about a new cheat yet, how do we write software to detect it? Historically, this has been a problem for game developers, because there are so many ways to cheat in a game that detecting all of them has become more and more difficult. Every time they release an update to detect a known cheating mechanism, it is only a matter of time before cheaters come up with a more creative cheat that completely evades detection. So, at some point, game developers decided, you know what? Let's fight these guys from the kernel itself. All operating systems, Windows, Linux, Mac OS, Unix-like systems, come with an internal component called the kernel. We have talked about the kernel before. I do not like redirecting people to other videos though, so here is a quick recap from a previous video of mine. In a computer system, we have hardware devices on one end. At the very opposite end, we have the user, whose goal is to run multiple applications. Dealing with hardware is actually very tedious and even risky, so to prevent applications from breaking things because of bugs or poorly written code, there is a very complex layer between user applications and the hardware. The very first part of that layer, the one that sits directly on top of the hardware, is what we call the kernel. The idea behind this design is that every time a user application needs the hardware in some way, the kernel manipulates the hardware on their behalf. User processes might still try to do things by their own, so extra protection is needed. For that reason, CPUs are designed to operate in two execution modes, restricted mode and privileged mode. When the CPU runs in privileged mode, it can execute virtually any instruction in its instruction set, including those required to configure hardware, manage memory through page tables, control interrupts, and communicate with peripherals such as GPUs, network cards, storage devices, and other I/O hardware. When the CPU runs in restricted mode, it is limited to executing a safe subset of instructions that do not allow direct access to hardware or critical system resources. In this mode, the processor can perform computations, comparisons, loops, and general program logic, but it cannot execute privileged instructions. Since privileged mode grants full control over the processor and system resources, the software running in this mode controls what restricted mode code is allowed to do. As you may have guessed, all user applications run in restricted mode, while the kernel runs in privileged mode. For that reason, we use two corresponding terms: kernel space and user space. When a user application needs to access hardware, for example, to display text on the screen or send a message through the network, it has no other option but to use a system call that invokes the kernel, asking it to perform the task on its behalf. This is the way modern systems ensure that normal user applications cannot directly access hardware, guaranteeing not only correct operation but also system security. In computer science, the kernel is like a sacred entity. Internally, it has a group of kernel-level subsystems that each manage a specific functionality of the system, especially functionality that requires direct access to hardware. Other software entities like user programs, which include games by the way, and even some components of the operating system, run in user mode. For a long time, the war between cheaters and game developers was fought in user space, because both the cheating software and the anti-cheat, usually as part of the game, were simply user space software. But eventually, game developers got tired and decided to move cheat detection software out of the game logic and into the kernel. Now, you might be thinking, if the kernel is part of the operating system, distributed by Microsoft, Apple, or whatever company makes the OS, how can game developers add something to it? The answer is drivers. You see, operating system developers, especially kernel developers, are in charge of writing the code that directly interacts with the hardware. The problem is that it is virtually impossible for them to write code for every hardware device out there, and they obviously cannot write code for devices that do not exist yet. So it is usually the device manufacturer's responsibility not only to distribute the physical device, but also to provide the machine code the operating system needs to handle that device correctly, and that is what we call a driver. By default, the kernel does not contain dedicated code to manage every possible device. When we install a driver, what we are doing is essentially adding an extension to the kernel so it can handle a very specific piece of hardware. And here is our answer. This same mechanism can be used to add all sorts of things to the kernel, including things that are not necessarily actual drivers for physical devices. Things like antivirus software, monitoring tools, or any other kind of software that could benefit from running in kernel mode. And why not? Anti-cheat software. And this is where we introduce a new concept: kernel-level anti-cheat, cheat detection software that lives in kernel space instead of user space. Since it has access to privileged instructions, kernel-level anti-cheat becomes much more powerful. From kernel space, it can inspect virtually every single user space process in a computer, far more of what the computer is doing, without many of the limitations it would have in user space. This means it can observe things before they reach the game, verify whether the game's memory is being accessed by another program, and generally make it much harder for cheats to hide. A normal user space anti-cheat can only see the system from the perspective of a regular program. It can inspect some files, scan parts of the game process, check loaded libraries, and look for known suspicious patterns. But if the cheat is more privileged, better hidden, or deliberately designed to avoid user space detection, the anti-cheat is fighting with one hand tied behind its back. Kernel-level anti-cheat is also incredibly useful when detecting cheating through hardware. Yes, I did not mention this before, but that is also a thing. Cheating can also be done through hardware. Imagine a cheater using some kind of physical sensor placed right in the screen. This simple photoresistor, connected to a microcontroller, is plugged into the computer through USB, and its only purpose is to signal a keystroke when it detects a change of color on the screen. This kind of thing is usually hard to detect from user space, because programs in user space can listen for a virtual representation of input events, but they do not have a reliable way to verify whether that input really came from the device the game expects. But if the anti-cheat is loaded and runs in the kernel, it has much deeper access to the hardware stack. That means it can inspect where input events are really coming from. This is also useful when a game enforces a specific set of input devices. Say a game policy requires players to play with mouse and keyboard. If a user tries to use a controller, mapping that controller inputs into keyboard and mouse inputs, a kernel-level anti-cheat would be able to detect that. So, as you can see, kernel-level anti-cheat kind of makes sense. If the anti-cheat software runs in kernel space, it can not only monitor suspicious software, but also suspicious hardware. And this brings us to the second part of the video. If the game's anti-cheat software resides in kernel space, why not put the cheat there too? As I mentioned before, cheaters are always trying to find more creative ways to avoid anti-cheat systems. And it turns out that cheating also becomes more powerful in kernel mode, because if the cheat runs in kernel mode, it can do virtually anything a computer can possibly do, not only to run the cheat, but also to try to hide itself. So, in more recent years, the war between game developers and cheaters, which started in user space, moved almost entirely into kernel space. For cheaters, though, it is not that simple. Software running in kernel space does not only have deep visibility into user space, it can also inspect what is happening inside kernel space itself. So even if a cheat runs in kernel space, it is only a matter of time before a kernel-level anti-cheat finds it. So cheaters had to get more creative, and that is where DMA cheats come in. The premise here is simple. If the anti-cheat runs in kernel space and has such deep visibility into the system, why not move the cheat to a different computer? Even if the anti-cheat runs with kernel privilege level, it will never be able to detect a cheat running in another computer. To make this possible, special hardware is needed. There is one big difference between a kernel extension made to handle a hardware device and a purely software-based kernel extension. I/O devices can directly access memory. Back in the old days, every time an I/O device needed data from memory, the CPU had to load that data and pass it to the device. That meant the CPU had to spend extra time and instructions handling the transfer as an intermediary. But modern I/O devices can use a feature known as DMA, short for direct memory access. With DMA, the system, usually through a small driver routine, can configure a device to read from or write to certain memory regions directly. After that setup, the device can transfer data without the CPU manually copying every byte. And this feature is what many modern cheats try to abuse. A special hardware device and its specially designed driver are installed on the machine where the game runs. The driver, which ends up being part of the operating system, will tell the CPU to allow direct memory access to the device. At that point, the device can be used to access memory regions related to the game and extract game information, like enemy positions, health points, cooldowns, and other useful data. Then, the extracted information can be sent to a second machine through some kind of interface, like USB, Ethernet, or another connection, even Wi-Fi. And it is on this second computer where the actual cheating software runs. This secondary machine can freely compute the game data to generate the overlays we talked about earlier, track enemy positions, calculate where to aim, compensate for recoil, predict movement, and decide when to shoot. Once those calculations are completed, the result can be sent back to the device connected to the gaming computer. From there, depending on the setup and the type of cheat, the device could try to influence the game in different ways. Remember, DMA can also allow directly write, so once the device receives the result of the cheat from the second machine, it could write modified values back into the game's memory, update camera angles, alter view-related data, or inject information into places the game later reads. Notice that the cheat itself becomes extremely hard to catch by scanning traditional patterns, because the most important part of it is not running on the same machine as the game. The anti-cheat can inspect the gaming computer as deeply as it wants, even from kernel space, but the actual cheating logic may be running somewhere else entirely. And if the setup is done carefully, the anti-cheat might not even see the data being forwarded to another computer, because that communication can happen outside the normal software stack of the gaming machine. There is an invisible boundary here. Kernel-level access gives the anti-cheat a lot of power, but it does not magically let it inspect a separate computer or everything happening behind an external hardware device. The main thing the anti-cheat can try to detect in this approach is the device accessing memory through DMA. But even that does not automatically mean cheating, because many legitimate devices use DMA all the time. For example, While playing a game, the GPU may need to access the game's memory to fetch assets like models, textures, or frame data. And this is where things get even more complicated for the anti-cheat. Once you enter this territory, there are many possible variations of the basic idea I just described. The device, for instance, does not even need to be a completely fake device. In theory, it could be a perfectly functional graphics card or peripheral that still does its normal job, but has been modified in hardware and firmware to do something extra in the background, not visible to the operating system. Also, this second computer, for example, does not have to be a $4,000 workstation. Cheats are usually just calculations, and almost any computer is good at that. It could be a laptop, a phone, or even a single-board computer like a Raspberry Pi or a compute module. My point is that if this secondary device is small enough, but still powerful enough for the purpose, it could even be integrated into the DMA device itself, a device that could potentially also function as a genuine GPU, capture card, network card, or whatever it is pretending to be. And now you know what those GPU-looking devices Riot Games shared the other day actually are. It turns out there is an entire black market around these things. Now, I will not talk about how those specific devices in the image work, mostly because most technical information about them can only be found in cheating subreddits and Discord servers. Anyway, something I would like to mention is that kernel-level anti-cheat is not completely useless against DMA cheats. It might not be able to directly identify the cheat itself, because again, the actual cheating logic is most likely running on a separate computer, but it can still try to find hints of it by analyzing system-level behavior or by directly preventing the cheat from working in the first place. I am not a Riot Games developer, and I do not know one, so take this with a grain of salt. But my best guess is that Riot bought some of these devices, reverse-engineered them, and then updated Vanguard, their kernel-level anti-cheat, to detect whether those specific devices, drivers, firmware signatures, or suspicious access patterns were present on a computer. I might be wrong, so if you work at Riot and want to potentially lose your job, let us know in the comments. Anyway, the only remaining question is, once the anti-cheat detects the cheat, can the game company make the cheater's computer unusable? Well, there are two ways to interpret the word unusable. The first one is physical damage, actually damaging the hardware so the computer or one of its components no longer works. The second one is software-level unusability, like preventing the user from using the computer until the suspicious device is removed. The first one is, realistically, not what we are talking about here. Yes, in theory, low-level software can interact with hardware in dangerous ways. Bad firmware and unstable device drivers can absolutely damage hardware, and kernel-level anti-cheat software has access to many of the same low-level tools that could cause that kind of damage. But intentionally destroying someone's computer would be insane from a legal, ethical, and business perspective. No serious game company is going to risk their entire business by intentionally make computers catch fire just because someone cheated in a video game. The more realistic possibility is software-level blocking. If an anti-cheat runs in kernel space and it detects something it considers forbidden, it have all the tools to do things like refuse to let the game run, force the user to reboot, block account access while the suspicious device is connected, or mark the system as untrusted. In a more aggressive scenario, the anti-cheat could go beyond simply blocking the game. It could push the system into a state where the computer no longer boots or functions normally until the suspicious hardware is removed, the configuration is repaired, or the operating system is reinstalled. In other words, it would not destroy the machine, but it could effectively sabotage the environment around it. From the user's perspective, that feels like the computer has been bricked, but technically, the hardware is still alive. The system is just being held hostage by its own configuration because something in that setup has been flagged and rejected by the kernel-level anti-cheat. And that is why people went crazy when Riot posted that on Twitter. Personally, I get the concern. I do not like this practice either, not because I care about cheaters, but because the software capable of doing this is being installed on millions of machines. And when you deploy software with that level of power at that scale, it is only a matter of time before something goes wrong and innocent users get caught in the blast radius. Also, there is a third way to answer this question, whether intentionally making someone's computer unusable is legal, but laws vary depending on the jurisdiction, so I will not go into that here. If you'd like to support the channel, Don't forget to check the sponsors in the description below. Or consider subscribing. And if you liked this video or learned something new, please hit the like button. It's free, and that would help me a lot. See you in the next one.